Hello, this is Getting Git, a talk that I gave at RailsConf 2008. Unfortunately, at RailsConf they didn't have recording set up for the sessions, and I've gotten a lot of requests to see this again, so I've decided to just go ahead and do the slideshow with a little voiceover. So, this talk is going to be largely about understanding Git internals and basic usage, and we'll get going. So, this is the layout of the talk for the most part. I'm going to spend a couple minutes going over what the talk is going to do. I'm going to introduce myself for a few minutes. And then I'm going to talk about what Git is to give you sort of a framework of how to think about Git. Then I'll talk about how Git works and then how to use Git on a day-to-day basis. And then I'll go over a little bit how to deploy with Git, both how to use it within Ruby in your deployed project and how to deploy with it via Capistrano, and where you can learn more. So, who is Scott? I am Scott Anthony Chacon. You can find my stuff at github.com/schacon, and I have a couple projects such as RubyGit, just Git bindings to Ruby, or Ruby bindings to Git, ActionScript Git, Ticket, and a whole bunch of other Git stuff. I'm the author of the Git internals PDF, published by Peepcode. I run gitcast.com. I'm the Git Capistrano module maintainer. And why am I here? It should be no surprise that via all that stuff, I'm here to talk about Git. So, what is Git? Git is a directory content management system, a tree history storage system, a stupid content tracker, and by that I mean it tracks content simply, and it's a toolkit. This is Git. There's about 150 commands that get installed with Git, but don't worry too much about that because these ones are generally not used by you on the command line. This is referred to as the plumbing. The vast majority of the commands that come with Git are meant to be used via other commands, not directly on the command line. You can use them. If you learn them, they can be really interesting and powerful, but for the most part, this is what you're going to use. And that's not quite as bad of a command set. This is called the porcelain, and these are the commands that you're meant to use on the command line. And there's about maybe 40 of them. About half of them you use the vast majority of the time. And we'll go over those in the other half of the talk. So, the last thing that you need to understand is that Git is not subversion, and it's really helpful in learning Git, to remember that it is not, in fact, subversion. It's not an evolution from RCS all the way through subversion, and Git is the next best thing, right? Some sort of linear progression. That's not what it is at all, and the sooner that you forget that, the easier it's probably going to be for you to learn to use Git and to use it well. So, I'm going to describe a source control taxonomy so you understand where Git fits in sort of the source control ecosystem. So there's traditional Delta storage source control management systems where your first commit, you commit an initial version of all the files, and then each subsequent commit, you commit a Delta, right? It keeps a patch or Delta, some sort of diff between that file and the previous version of the file. The other type of source control management system is directed to cyclic graph storage or sort of snapshot storage or tree storage, where it stores a new version of the file each time that you commit. Okay? So the advantages to Delta storage is, of course, that these are much smaller, and so it's a little more efficient to store generally than these are. But there are ways to get around that, which we'll see a little bit later. So there are different versions of these. There are local ones that only work on your local machine, centralized versions that have a centralized data store that everybody commits and pulls from, and distributed versions. So local Delta would of course be RCS, which many of you are probably familiar with. Centralized systems would be CVS, Subversion, Perforce, which are all sort of built on top of RCS as a storage mechanism. And distributed versions of these are Darks and Mercurial, and so for those Mercurial fans or people who have heard about Mercurial, that is what it is. It is a little bit closer to RCS, CVS, Subversion, and then Mercurial. Git is different. So probably the most common local tree storage is copy-r. This is probably the most commonly used source control management system out there. A more sophisticated version of that would be Time Machine, which actually uses hard-linked files rather than copies of every file. It hard links files that are identical, so it doesn't reuse disk space. A slightly centralized and basically distributed snapshot storage system is BitKeeper, which is commercial and was used for the Linux kernel for a while, but you cannot use it without a centralized server, so it is somewhat centralized. And then fully distributed versions are Git and Bazaar. Now, how does Git work? The heart of Git is the Git directory. And by default, that's .git, but you can overwrite that by setting the git dir environment variable at any time. And there are only one of these. It's not one per subdirectory like Subversion or CVS, but and it doesn't need to live in your project directory either. If you overwrite the git dir environment variable, you can put it absolutely anywhere. You can put it outside your project tree. It doesn't matter as long as Git knows where it is. Now within this directory, which is basically your repository, you have a configuration file that has per this repository configuration settings. You have hooks, which are sort of pre and post action hooks of some sort. They're simple shell scripts. An index file, which we'll get into in a minute, an object database that stores the content of the Git repository, and references, which we'll also mention in a moment. So the first thing is the object database, which stores your content. Now this can be any content. We'll go over the different types in a minute, but basically what Git does is it appends a header to that content, which is a simple type, a space, the size of the content, and a null byte. And it just appends that to the content to give you sort of new content. And then Git will get the SHA-1 of that content, and that'll give you a 40-character SHA string. And you're going to be referring to that. This is almost like a block pointer. You're going to be referring to that for the lifetime of this object. Then Git will zlib deflate that content to give you a compressed version, and it's going to create a path out of that SHA by chopping off the first 2 characters and then having a file name as the last 38 characters and writing it into this directory. And then it'll write that file, the compressed version of that. So every object in Git is compressed and written to disk in this manner. This is referred to as a loose format. So when you hear people talking about loose objects in the Git database, it means that they are in this path. Okay. Now, if you run a garbage collection on Git or you do regular maintenance on it, which can happen automatically depending on your version of Git, Git will go through and it'll take different files that have minor differences. So say these are all versions of the README file that just have a very small difference. We're keeping entire compressed versions of them, even though there's maybe a new line or a one-line change on each one, and we're writing them all to disk, so that's wasteful. So what Git will do is it'll find all of these blobs that are pointed to by the same file name, it'll delta compress them, and it'll write them into a pack file. And then it will remove the original files. And you have a pack file and an index file. The index file just has pointers into the pack file for where to retrieve each individual version of this file. And so this is how Git has very efficient data stores. So this is referred to as the packed format, these pack files. And so all of the objects in Git are stored in this way. They're either packed or they're loose. Now, there are 4 types of Git objects. There is the blob, the tree, the commit, and the tag. If you have a working directory with a bunch of files and subdirectories into it, every file will be turned into a blob in the Git directory. Okay? So that consists of just taking the content of the file, appending the header to it, compressing it, and writing it to disk. It's very simple. It's just the content of the file. The second type is the tree. If every file in your working directory is a blob, then every subdirectory, or every directory, really, is a tree, including the root. So within a tree, it is basically like a Linux directory or a POSIX directory listing, where you have inode information and a file name that content is going to be checked out as. In POSIX directory listings, you'll have an inode number, a pointer into an inode tree, that table that you can look up this information, but since there's not much stored, that it just writes it directly into the tree listing. So we're storing the mode, the type, which is always either a tree or blob, and sort of the block pointer, which is this is actually 40 characters, is the SHA of the file, either the subtree or the blob that you're going to pull out of the Git directory. The third object type is the commit, and that's simply a pointer and some meta information to the root tree of a directory that your content is stored in. And that consists of a commit object, a commit message, an author and a committer and date stamp for each one, which are often the same, a parent, which is one or more parents, or actually zero or more parents. So that is a pointer to the previous commit or commits. So if it's a merge, you'll have several of them. If it's the first commit on a tree or on a history, then you will have 0 of these. And then the initial tree pointer. So that is your directed acyclic graph. You have commit that points to 0 or more of its ancestors, and one tree, a tree which points to many trees and blobs. The fourth object type is a tag. And a tag is simply a pointer to a single commit. And that has a message, a tagger, name and date, what the tag is, and the object that is tagging. And most of the time this will be a commit, but you can also tag other things. So those are your 4 object types. They are immutable. They can never be changed. Whenever you do a rebase or you're doing something that say changes your history somehow, it's not actually changing any of the commits, because that would change if you change anything in any of these object types, and the SHA changes, right? So what this actually does, what it normally does, is that it writes a new object and just sort of ignores the old ones and leaves them in the database. So these can never be changed. Now, the other thing in the Git directory that we're going to look at next is references. Because tags can't be moved around, we need something that can. We need to be tracking where the head of our branch or our remote is at any time. And so these references are used for that. They're lightweight movable pointers to a commit. And they're stored in .git directory under the refs stuff. Normally, so all the branches are stored under heads, refs heads, and all the remotes are stored under refs remotes. And all the tags are stored under ref tags. So basically all that is a file with 40 characters written in it. It's just the SHA of what it's pointing to. And rewriting that, changing where a branch is pointing to, is simply rewriting the 40 characters. So that's our object model. So let's go through a scenario. Let's say that this is a tree that we've committed into our object directory and into Git, and we change the file that this blob is representing. Okay. Now that's going to change every tree above it, because we have to write the new content of the blob into the directory. We have to write the tree that points to it, because it has a SHA that's been changed within it. And so when we have to write in a new tree that has that new SHA reference, which changes its SHA, right? So the tree above that has to change the SHA that's pointing to that, and so on and so forth. And then we write in a new commit object, because we do so every time we do a commit. Then we move the branch head forward, which is just rewriting the 40 characters in that file. And the head is pointing to that branch, so it automatically moves forward. So the tag, or we can write in a tag at this point, and that's not going to change. And you can see that we've reused these blob objects. Now, the interesting thing is that these SHAs don't change, so we don't have to rewrite these files in again. So it's sort of like hard linking in like a POSIX directory structure. So let's say that we change the blob that this one's pointing to. Well, all we have to do is write in the new blob, right? And we have to write in a new tree that points to it, but we don't have to write in this tree again. So Git sort of does like a hard linking thing, where if nothing in a subdirectory is changed, we don't have to write that subdirectory in again. We just reuse the SHA. Okay. So if we copy a subdirectory and rename it something else, all Git will do in the tree that references it is put the same SHA with 2 different names on it, and we don't have to use up any more disk space on that. So these are the 16 objects that are immutable, that are written into our object directory to do our 3 commits, and we can pull out this tree or this tree or this tree at any time. So how does it actually pull those out? Well, when we do a checkout, and we give it a tag name or a branch name or a remote name, and it goes into our refs directory and looks for a file that matches that under one of those directories. And in this case, it finds a tag, and it takes normally it's 40 characters, but I'm doing a short one here, and it'll go in and it'll find the object that has those 40 characters, and it'll pull it out. And in this case, it has a pointer to a commit, so it pulls that commit out, which has a pointer to a root tree, which pulls that tree out, which has 3 pointers in it, 2 blobs and a tree. So it pulls that blob out and names it rake file, pulls this blob out and writes it under the readme file, pulls this tree directory out, which has a pointer to 1, and pulls this blob out and writes it under lib/simplegit.rb. So that's how the walking of the checkout actually happens. Now, for the commit history stuff, I'm going to be representing this entire DAG as this one object. So when you see these objects, just think of all the trees and blobs that are underneath it as well. So here's an example of branching and merging. So let's say that this is our original, we have two commits, we have a master, a branch that's pointing to the head of our commit here, and a head which is saying which one we're currently on. And we do checkout-b experiment, which does two things. It creates a new branch and it checks it out. So we've created an experiment branch, you can see here, and our head is moved over to it, which is what happens when you do a checkout. So that means all future commits will be moving this branch forward instead of the master branch. So now we do a commit and it's moved the experiment branch forward. We do a commit again, and it continues to, every time it writes a new commit in, it moves our experiment pointer with it. Okay, but we can see that our master branch has not moved. It's still pointing to the old one. So if we check out master, basically what that does is it makes our working directory look like the older tree and then moves our head over. And then we can run commit, and that will now move the master branch forward instead and have the one that master was pointing to as the ancestor for that new commit. So we can tag, that'll tag it there. We can go back over to experiment and commit again, edit something, commit again. We can go back over to master and merge in the experiment branch, and that's how you have, that's sort of the workflow in which you would get a branched and merged history. Okay, so let's look at remotes for a minute. If you clone a remote, so let's say that we've cloned a remote, they just have this one commit. We've named it origin, so their master branch is on this commit. Our master branch is now on this commit, and we start working. Okay, so we do a commit, our master branch moves forward. We do another commit, our master branch moves forward, and now at this point we fetch from the origin. Okay, so what that's going to do is it's going to pull down all the work that they've done in the mean. We've added 2 commits since we cloned, but they, in this case, have added 4. Okay, and they branched, and so they have an idea branch, and then they have their master branch, which has 3 commits on it. And at this point, let's say we can inspect these objects, right? We can look and we can see, oh, I like what they've done with their master branch. I like what they've done with their idea branch. I want a new tree that has all of those changes in it plus the ones that I've done. So now I can check out a new branch called try idea, and I want to merge all these 3 together and try it out without moving my master branch around because it may not work out well. And I run merge origin master origin idea, and that does a 3-way merge. So all the changes that they've done on their idea branch, on their master branch, that I've done in the meantime are all in one new tree. Okay. And if I don't like it, I can always just delete my try idea branch, remove my origin, and I'm back to this, right? I don't need to lose anything. It's very easy to experiment, to try stuff with branches in Git, because you can always just leave one behind and go back to it if you need to. So, remote workflow. A very simple example. What's very common in Git is that all the players have a local repository, a private one that they use personally, and then they have a public repository that they'll push into for other people to access. It's a very common one, and a lot of times everybody will have their own public repository, like a personal one for all their projects, a personal one for each project, and then a local repository for each project. And so in this particular case, let's say that we have a couple of objects, A, B, and C here, in our local repository, and we want to share them with people, so we run git push, generally over SSH when you're pushing, and it pushes those objects into our public repository. Now somebody is interested in that, so they do a clone or a fetch. It pulls those objects down into their local repository. Now they can commit there locally, and then they can push out into their public repository, and then I have the option of adding them as a remote and pulling those objects down. And then if I like them, I can merge them in, I can push them back out into mine. And so it's cyclical. That's generally how a workflow goes between 2 people. Now, multiple remotes. Let's say that we have 2 people that are interested in this, Nick and Jessica, and I have this simple one commit and a tree, and it points to 2 blobs. So this is basically just a directory with 2 files in it. Now I create a public repository, say on GitHub, scachacon/project, right? And I push into that, and I call it public instead of origin, because the names of these things actually don't really matter. And so in this case, I'm just going to call it public. So I'm going to push in that. Nick's going to clone from that, and you can see he gets the same 4 objects. and he commits where he's changed one of the objects. Okay, so his new commit just adds 3 new objects into it. Now Jessica clones, and she actually changed 2 of the files, so she gets 2 new blobs, right? Whereas Nick only added 1 new blob. Now they've sort of branched off from each other, okay? So they can push into their own public repositories. Now I have the option of pulling those changes in. So how do I pull them in and merge them with mine? Well, I add them as remote. So if you do git remote add, and then the handle that you want to use for that, and then the URL for that, I can name it anything. So you can see I'm not naming it Nick H because that's what the project name is, right? I'm naming it Nick. That's what I want to call it. It doesn't matter. You can name it anything you want to. And then I do the same for Jess, right? So I add her as a remote too. Now I have this little handle I can use. So I can say git fetch Nick, and it knows that Nick means that entire URL that I just added as my remote. So it goes and it pulls all those objects down that he has that I do not have yet. So it just does the diff. And then it gives me a pointer to where his master branch is. And I can do the same with Jess and pull all the objects down that she has I don't have yet, and give me a pointer to where her master branch is. And now at this point, let's say I want to use one of his objects and one of her objects, right? I like one of her changes on one of the files, and I like his change in the other file. So I do a merge. I do git merge Nick Jess, and I choose one of his and one of hers, and I write in a new tree and a new commit. Okay, so I haven't added any new blobs here, but I've added a new tree and a new commit, and I've moved my master branch forward, you can see. And my public master, you can see public master there, is back where last time I pushed. So if I push again, that moves forward, and I have pointers to where all of our master branches are. My public directory has all of the objects, and you can see how Nick's objects have propagated through the ecosystem, and you can see how Jessica's objects have propagated, and now mine have. And now if Jessica fetches, she'll get all of Nick's and my changes, and if Nick fetches, he'll get all of Jessica and my changes. So I hope that makes sense. Another thing that we can do other than merging is called rebasing, and a lot of people have a little bit of a hard time understanding what this does, so I'm going to try and explain it as simply as possible. So let's say that I have 2 commits in my tree, or in my history. Jessica has clones from me, so she gets the same 2 commits. Okay, now we work independently, and we both add a couple of commits, and our master branches move forward. So now I want to pull in her changes. So I do git fetch Jess, and it creates a pack file of the commits that I don't have yet, and all the objects and stuff that I don't have yet, and it pulls it over into mine and gives me a pointer to where her master branch is. Now, at this point, I want to merge these changes together. I want to take the 2 changes she's made and the 2 changes I've made, and I want to make one new tree out of it. So I can run git merge, and that will add a new commit automatically that tries to automatically merge the trees together. If there's no conflicts, then it just automatically creates it. If there are, then it makes me resolve them, and then I can go ahead and commit that. But that's called a merge commit because I don't introduce any actual new work. I just merge stuff together. Now, the other way of doing that so that you don't have this split and then sort of diverge and then merge history going on is to do what's called a rebase. Now, what a rebase is it takes the 2 changes that you've done and sort of ignores them, creates 2 brand new commits that have an ancestor. Instead of to the point where you split off, it has its ancestor to where the tree that you're or the commit that you're rebasing to is. Okay, so basically what it does is it takes the point at which you diverged, it creates patch files from the 2 changes that you've introduced, and it applies them to the new head that you want, right? To Jess last master in this case. So it'll apply the change that I introduced from C2 to C3 and add it onto C6, and then the change that I introduced from C3 to C4 and adds it onto my new C3. So it basically just creates 2 new commit objects and moves them onto the top of what I'd like to merge in. Okay, so now instead of the merge history, we have a nice linear history that looks like I started working where she left off rather than us working in parallel. So the tree-ish. So now there are different ways that we can refer to commit objects in the database. In fact, there's a lot of different ways that we can refer to not just commit objects, but also other objects in the database without having to list out the full SHA. So the easiest way really is to just do not the easiest way, but the most straightforward way is to do the full SHA, the 40 characters that represent that object in Git. Okay, but that is super annoying. So other ways you can do it is a partial SHA, right? You can do anything that makes it unique. So if the first 5 characters are unique to that SHA, which is very common, it's very uncommon for 2 objects in the Git directory to share more than the first 4 or 5 characters. But as long as it can figure out which one that you're talking about, it doesn't really care how many of the characters you put in there. You can also use a branch, remote, or tag name because it can find that file in the refs directory, and that has the 40 characters it's looking for. You can use a date spec, which says, I want to know where my master branch was yesterday or a month ago. The problem with this and with the ordinal spec is that this is different on different people's computer. Where your master branch was yesterday may not be where somebody else's was. In fact, probably won't be where somebody else's was. Whereas the SHA stuff is always going to be identical on different people's computers. Okay, so I'm sorry. The ordinal spec is the 5th prior value of master. So again, this is different on your computer than somebody else's. The caret parent means the second parent. So if you have a 3-way merge, you have 3 different parents on a commit. So you can either do tilde, which is the first parent, tilde 2, which is the second, tilde 3, which is the third. If you if you don't have a merge, if it's not a merge object, then this doesn't make sense. So you really only use these for merge commits. Tilde spec means the parent of the parent. Okay, so it's like a grandparent. So it just does. It's the first parent of the first parent. So we'll do an example of that in a second. Tree pointer means you give it a ref spec for a commit, and then you do tilde tree, and that says I want the tree object instead. So that's useful if you're running ls tree or something that's specifically looking for a tree object. The blob spec will give you a certain version of a file. So this will point to the blob of that file in that commit. Okay, so if you're looking for a specific version of a file, you can do like a tag like v1.0 colon and the path of the file. That'll give you the version of that file in that particular version of the commit. So you can also do ranges. So if you want everything in between these 2 commits or something, you just do 2 dots in between them, and you can use any tree on either side of that. Or if you want everything since, you can do the 2 dots after, or everything until, you can do the 2 dots before. So those are some common examples of some of the shorthand ways you can refer to objects in Git that you'll see occasionally. So here's a couple of examples of what that actually means. Master tilde, I'm sorry, I did the same thing in my actual talk here. Master caret will tell you the parent of the object that you're pointing at. So if it's master, it'll be the parent of the master. So the caret 2 will be the second parent. Okay, so there's a first parent, there's a second parent. So if it's a merge, you can refer to either of them. Now, the difference between caret 2 and tilde 2 is that tilde 2 is, so this is caret 2, this is tilde 2. Okay, it's a parent of the parent rather than the second parent. Now, you can also do more complicated things. You can string them together. So these 2 things are actually identical. Both of these refer to the second parent, or sort of the grandparent, and then, the parent of the parent, and this one refers to the second parent. So that's actually the flow of either of those. Those mean the same thing. And then you can do ranges. So everything in between the third grandparent and the first parent. Okay, so local stuff. Let's go over the index for a minute, because this is the other important thing in the Git directory, and it's important to understanding how git add and git commit work. So you have 3 major things. You have the working directory, you have the index, and you have your Git repository. Now, what git add does is it takes changes in your working directory and stages them. Okay, so it puts them into this, it puts references to them into this index file. It does not actually add them to your repository. It just stages them. Commit will take everything that you've staged with git add and actually add it into the repository. Okay, so what does that mean? Well, if we have our working directory under, say, project, we have our index would be by default under the .git directory as the index file, and our object directory by default would be in .git/objects. So let's do a checkout. It's going to take all the blobs so it'll walk down the master branch, it'll take the blobs that it finds, and it'll check them out into the index. So it gives us references to what the version is in Git, what the version is in our staging environment, and what the version is in our working directory. It'll store the modified times of the file so that it can see when it changes easily, and then it checks out those objects into the file names. So let's modify one of the files. Now when we run git status, it's going to update our index so that we can actually see that now the version in our working directory and the version that is staged are different. So when we run git status, it's going to put our file that we've modified into this category, changed but not updated. This means that it has been changed in our working directory, but we have not staged it yet. Okay, so if we run git add, that actually stages it. Okay, so that updates our all that does is update a reference in our index. So that says, okay, they've marked this to be staged. So our next commit is going to include this file. So the staged version and the working directory version are exactly the same. And it also actually adds the blob into our object directory at this point. So if we modify it again and then add it again, that version is just ignored. It'll be pruned the next time that we run git gc prune or something, but it does actually add it into the object directory at the point at which you run git add. It just doesn't have anything pointing to it yet. So if you run git status at this point, it's going to see that your staged version and your git directory version are different. And so that means you have a file that has been modified and staged but has not been committed yet. So when you run git status, you'll see that file come up under changes to be committed. So if we actually run git commit at this point, it's going to update our version that we have pointing to in our git directory. It's going to write in our tree and our commit, and it's going to move forward our branches. All right, so let's modify two files now. So we've changed file 1 and file 2, and we run git status now. Okay, now both of these have been changed, and if we run git add on one of the files, so we've changed two of them, let's run git add to stage one of them. Okay, so now this one's staged because these two are the same. This one is not staged, but it's modified because these two are different. So when we run git status, we're going to see that this file is staged, changed to be committed, and this file is not. So our next commit is not going to include this file. Okay, so when we run git commit, we can see that we've just added this single file to it, and we've reused the other one. So that's how the index works. It's a simple file that just keeps references to what is staged and what is modified and what's in our git directory, and helps us figure out what is going to go into our next commit. So how do I use Git? There's about 152 total commands, or about 150. This is what I found. About 40 of them are porcelain commands. So these are the ones that we're going to be running on a daily basis, right, generally. And we're going to go over about half of them, which are the ones we use most of the time. Now, getting Git, you can retrieve Git source code from git.org.cz. Just, copy the tarball, make install. You can install it via package manager as well if you'd like to. Although I would recommend that you get it from source code if possible, if you have compiling tools, because they're making a lot of usability changes a lot, and so generally you'll get a slightly nicer usable version, the newer one that you use. So let's set it up. The first thing you're going to do when you install Git is that you're going to run git config -- global user.name and user.email, because that's going to be the name and email that are going to be used by default on all of your projects for your commits. Okay, because it writes your name and email into your commits. This is what it's going to use. Otherwise, it's going to try and figure it out, and it looks horrible, and you don't want that. So be sure to write that. The -- global writes it here, so it writes it into your home directory .git-config file, and that's used for the default values of all of your Git directories. You can also overwrite that and the config file in your Git directory. So that's git config. Getting a repo. Generally you'll run git clone to get an existing repo. Now there are different protocols that this will run under. SSH, HTTPS or HTTP, the Git protocol, like you can do local files, you can use rsync. I would ignore rsync for now since most people don't use that. It's sort of deprecated. You'll generally push over SSH because that is a secure, authenticated, easy to set up protocol, and you'll generally pull over any of these three. The Git protocol is unauthenticated. HTTPS you can push over DAV. It's a little hard to set up. And a local file, unless you have some sort of NFS mount or something, it's generally not used. So these are the common ones you'll pull over, and this is the common one you'll push over. Okay. So in this case, we're cloning over the Git protocol. So what it's going to do is it's going to connect. It's going to generate a pack file on the other side. It's going to pull them down and check them out. So you can also initialize a local repository. So just go into or a repository on an existing project. So go into your project, run git init, which creates the .git file, the .git directory. Git add adds all your files. Git commit will put in your first commit. So let's see this. We run git init, initializes git repository.git, git add. We'll add everything. It doesn't really give you an output. And then git commit -n specifies the commit message, although you can not leave that off and it'll open up into your editor. And we can see that it added the 3 files, and there are 3 insertions, right? So that's fairly easy. That's a very common way to initialize a Git directory. So normal workflow, the first thing that you're probably going to want to do is add your .gitignore file. So this means that you're going to want to add in any files you don't want Git to put in by default. So temporary files, log files, database. I mean, this is a general setup for Rails environment, for example, but whatever you want Git to ignore, you want to put into this file first. So if we run git status and we've modified these 2 files, we add the readme file, we can see that now the readme file is staged and the to-do file is not, right? And that means we've added the readme file to the index. If we commit at this point, then we run git status again, we can see the readme file isn't there anymore because it's in our directory now. It's in our repository now. So now we've added the index and then we've committed that index into the repository. So just a review of that. So git log. This is a really helpful way of looking at your history. So this is your commit history, okay? It's going to give you the last commit that you did and the commit before that, and for each commit it's going to do the SHA of the commit, the author, the date, the message, and so on. There are different ways you can format this output. You can use -- pretty equals 1 line to give you 1 line per commit, which just gives you the SHA and the stat or the commit message. You can do a format, which you can format however you want to. In this case, I did a partial SHA and then the author name and then the date and the message. You can also do diff, which is an interesting way of seeing the differences between 2 trees. So in this case, it'll give you a unified diff output. Okay, and that is a real diff. So you can do git diff and pipe it into a diff file, and then somebody else can apply that with patch. Or you can run git apply, and they basically do the same thing. So the other way that you can generate and apply patch is through format patch and git-am, which makes an email formatted patch, something that can be sent over email easily, and that retains the commit message and the author name, email, and date. So you can git-am will actually create a new commit and retain the commit metadata. Okay, so this is the way that a lot of patch files are done on projects that like to accept patch files over Git. And the way you do that is git format patch. Basically it'll take the diff arguments, and then if you do -- standard out, you can pipe it into a file. Otherwise, it'll create a directory and write those files to disk. And then you assign those to somebody, and they can apply it with git-am. The other way you can do multiple of them is if you say -o patches, it'll create a directory, write all the patch files into their 1 commit per file, or 1 file per commit. And then you can use send email to email all of those patches to a listserv or something, and then you can somebody else can download those into an mbox and run git-am on that mbox. So let's look at an example of this. If we wanted to patch Rails, this is actually how Rails has asked to have patches sent into them. You clone the Rails directory, you go into that, you make your changes, you run format patch on where you had cloned it from, and output it into a patch file, and then you upload that patch file to Lighthouse, which is their ticket management system. And then somebody else can download that patch file and run git-am and pipe it in. And that's how Rails accepts patches, and that's how that workflow is supposed to go. So, branching, merging, and rebasing. A general workflow for working with Git is to have a master branch, which is, this is just a convention, but it's a common one. So in general, you have a master branch that is stable. So only stuff that would go out into production basically goes into this master branch. And you have a development branch or something like that it's like a trunk, right? It's where you do integration, it's where you test out stuff, it's where it's for you to work on. And then occasionally, as you become stable, you merge that into your master branch, okay? So it's also very common to have topic branches, which are short, medium-lived branches. A lot of times these only last an hour or a day. You create a new topic for a new story if you're doing like a Scrum thing or a new feature that you're working on, and then as soon as it's done and stable in the test pass, you merge it back into your development branch. And that's how you're sort of continuously working on stuff. And you can have several topic branches, and they can be long running. If you're, say, migrating from Rails 1.2 to 2.0 or something, you might have something that's continuously out there that you're occasionally rebasing master back into, and then eventually you merge back into your development branch. Okay, so a way to think of this is that your master branch is like your production branch, and your development branch is like your trunk. Okay, now this is just a convention that I see a lot. You do not have to do this. You can come up with your complete own workflow. It's totally up to you, but this is one of the advantages of having cheap branching and merging. So let's look at a workflow with this. So we're doing normal development. So if we run git branch, it'll show us our branches, and it'll put a star next to the one we're currently on. So we're on a development branch right now. If we run show branch, it's a different way of viewing this information that shows us the last commit on each of our branches that we have. We can see the same 3 branches and sort of what's happened since we've all diverged. So on story 95, we have 2 commits since we diverged, and on develop, we have 2 different commits since we diverged, and they're not in common. So graphically, this looks something like this. So now we want to try out an idea. We can check out -b an idea, which does 2 things. Again, it creates a new branch called idea, and it checks it out. So if we run git branch, we can see that we're on the idea branch now. So it does basically just that. Now we modify a file and commit it. Okay, so now we can see that we've created a new commit with that new tree, and our idea branches move forward because that's what we're currently on. Now, let's say that the pointy-haired boss comes in, we have to do a hotfix. Okay, we can go back to our master branch. Excuse me. We can go back to our master branch because that is where production is, and we can make a change. So we can see we're on our master branch, we make a change, we commit it, we tag it because it's going into production, and now we can see that we've gone back to our master branch and we've made a new commit. So let's merge our idea branch at this point. So we go back out into our development branch because we've pushed that out into production, and we merge in our idea branch that we had because we think that it's cool, it's been peer reviewed, whatever. It does a fast forward, and that just moves our development branch forward to where our idea branch was. So now we want to push that out to production. So we go back to our master branch, which is where our production code lives, and we merge in our development branch, and that's it. Okay, so it's fairly simple. The other way that we could do that is to go back to our master branch, and we can rebase our development branch. And what that will do is this. It'll take our changes that we had on our development branch and the hotfix that we did and stick it on the top and just ignore the older one that we had. Okay, so these are the 2 different ways that a merge and a rebase would look in that situation. So let's go over that again really quickly so you can just kind of see without all the command line stuff what was happening. So check out -b idea gives us a new idea branch. Commit, we'll move that forward and give a new commit. Check out master goes back. Commit, we'll move that one forward. Check out idea, merge develop, we'll move the development branch forward. Branch -d idea, we'll delete the original idea branch. Go back to our master, merge and develop. So that's a common workflow that you might see a lot. So we've gone through most of them now. Let's go through the last couple ones. Sharing Git. So let's say you run git remote, nothing's there. You don't have any remotes in here, so you can't push or pull to anybody. Okay. If you go to GitHub, for example, this is the easiest way of showing how to set up a public repository, and you create a new repository, type in this case, simple git to anyone can see it. It gives me a new project, right? So now I can take this push URL and I can run git remote add, whatever handle I want to call it, and then the URL that I copied off the website. And then if I run git push and then the nick that I gave it and then the branch that I want to push out, in this case master, it will take, here it says master branch on GitHub used to be nothing and now it is this, right? So now I've pushed out, and if I say git remote, I can see that I now have public, right, which is the nick that I gave it. And if I run git remote show public, I can actually see the details of that, what the URL is, if there's a tracked branch, etc. So now if I go back to GitHub, I can actually see my new project. I can see that the files were pushed in. I can see that it has all my information here, and I can take this clone URL and I can give it to friends and family and say, go ahead and run this, and they will get a copy of my project. So let's look at distributed workflow for a minute. One more time. We run git remote. We can see our remotes. In this case, GitHub, which is probably a GitHub account. We can run git remote show GitHub, and it actually shows us what the URL is. And we can see that it's over the Git protocol, so we can't push to it because Git protocol is unauthenticated. And we can run git fetch GitHub, and it'll pull that down. And if we run git branch -a, it'll show us all of our branches, including our remotes, which it doesn't do by default. And so we can see we have the master branch on our GitHub remote. Now we can run pull. Now pull is just a fetch plus a merge. So it's not more complicated than that. The opposite of a push is not really a pull in Git. The opposite of a push is closer to a merge. I'm sorry. The opposite of a push is closer to a fetch. So when you do a pull, when you do git pull something, all it does is it fetches all the objects and then it merges in the changes automatically. So a lot of times I won't do that. I'll just fetch them and I'll merge them manually. So push will actually push the objects, which we just saw, but we'll go over it again really fast. We can see that the git at github.com instead of git : / means that this is an SSH account. If it doesn't have a : / in front of it, that generally means that that Git thinks it's going to be an SSH account. So unless it specifies the protocol, Git will assume SSH. So in this case, this is the Git user at github.com, and it's going to use SSH. So this means we can probably push to it. So if we do git push public master, that will push our master branch out. So now we've gone over the 20 or so that we really need to use Git on a day-to-day basis. So let's review them real fast. So git config sets up our configuration variables. Git init initializes a Git directory. Git add will stage files. Git commit will commit our staged files. Git status will show us which files we have modified and staged in a working directory. Git tag will add a new tag object. Git log will show us our commit history in several different ways. Git checkout will switch our branch that we have and make our working directory look like it. Git branch will create a new branch to show us which branches we have. Git merge will merge a branch into what we currently have checked out, or several branches into what we currently have checked out. Git rebase will do the same thing, only it writes the history differently. Git remote will show us our remotes or add or delete, add new ones or delete existing ones. Git fetch will fetch objects that we don't have from a remote. Git pull will fetch the objects and then merge them into a tracking branch. Git clone will do a number of things. It will actually do a git remote add. It'll add in a remote. It'll do a fetch on it, and then it will check it out. But basically, you can think of it as just copying a directory, a Git repository. Git push will push a branch into a remote that we have write access to. Git diff will show us a unified diff of two different trees. Git apply will apply that diff to our current tree. Git format patch will give us an email formatted diff, and git am will apply that and create a new commit object. So these are the 20 or so objects or commands that you're going to need to know in Git to do most of the stuff that you're ever really going to do in Git. So popular workflows, let's go over that for a second. Central repository model is sort of like a subversion workflow. So this is actually very common in Git as well, and don't be afraid or embarrassed to use this. It's a good way of keeping people in sync. How this works is everybody has a shared repository, maybe over SSH, that they all have write access to, and everybody get clones from it. Right? This is often used in a private environment or something, and then a developer can push to it. And then if a second developer tries to push to it, they're going to get rejected, right? Because it's going to say it's not upstream from you. So that developer then has to do a fetch, do a merge locally, and then push. Okay, so that ensures that everybody sort of stays in sync, because they can't push until they pull something if somebody else has. So that's one very common model even in Git, because a lot of people are used to that from Subversion as well. So dictator and lieutenants model. This is how the Git kernel generally works. And other very larger projects kind of work this way, where there is a person that's sort of in charge of the whole project, and then a number of lieutenants in charge of various subsystems of the project, and then a bunch of developers. And so the developers will clone from sort of a blessed repository. In the Linux kernel case, that would be Linus's Git tree. it could be whatever, however that convention's set up within that community. Now, all the developers will clone. One lieutenant will fetch or receive patches from a subset of the developers that are working on their subsystem and merge them locally, and another lieutenant will do the same thing with their developers. And then the dictator only has to deal with his lieutenants. So he can fetch and merge stuff that has already been aggregated for him or her and merge them locally and have sort of the definitive repository and then push it into that, and the cycle continues. So another common model is sort of an integration manager model, which everybody has a public repository and a private repository and shares them with each other, but there is sort of one main repository that is counted as the definitive repository. Okay, so a common example of this is what the workflow is on GitHub. So in the case of ticket, there's some people that have forks of my main ticket branch and may add a new patch in every once in a while and then ask me to pull from it, and I'll do that. So the basic way that workflow goes is that I'll push into my repository, people will clone from that, maybe make a change and push into theirs, maybe share with each other and push into theirs, and then I will add them as remotes, fetch those objects, rebase or merge them, and then push them back up into mine, and that cycle will continue. So, how do I deploy with Git? We're at the end of the talk. You can use Capistrano to deploy Git projects that are stored in Git very easily. There are only two main places, really, generally, that you have Subversion embedded in your deploy.rb file. Your repository is going to have something Subversion specific you're going to have to replace with your Git repository, and your SCM might be set to Subversion. So you're going to want to replace your repository with something that is your Git URL and set your SCM to Git. And that's really all you need to do to make Git deployments work in Capistrano. As long as you can SSH to your server and run git clone, it should work fine. The other thing you might want to do is run git set deploy via remote cache, because by default Git will do a clone every time instead of an SVN export, because there's really no equivalent to SVN export. I'll go over something that's close in a second, but you might want to do deploy via remote cache so that it clones it the first time and then just runs a fetch every time after that. Now, other options for Capistrano you can use with Git is to set the branch to something different. You might have a deployment branch, you might have a production branch. I believe by default it's master, but you can set it to something else. Now, you can also run git shallow clone. This is something that's similar to SVN export. It just does a clone of, n parents. In this case, I've set it to 1, so it'll just do a clone of the first tree that it finds. This is a good option. If you can't do deploy via remote cache for some reason, although you cannot use it in conjunction with deploy via remote cache, but I would use deploy via remote cache if that's possible. Now, the other thing you can do is git enable submodules, which if you have submodules in your project, we'll actually check those out as well. So, Ruby and Git. There are certain ways that you can use Git within your Ruby project programmatically. They're sort of bindings, not really bindings, but they're sort of wrappers to the Git protocol or reimplementations of Git. There are 3 of them that are main ones. One is Grit, which is used in GitHub. One is the git-scm, which I've written. These are both system call wrappers around Git. And then there's Git Ruby, which is a pure Ruby implementation of Git that I also wrote, but it's not as full-featured. So I'm going to go over the git-scm only because I'm more familiar with it, and it has write access. You can actually do commits and write trees and read trees and some more low-level stuff as well, whereas Grit is a read-only library. So the way that you would use it is just gem install Git, and then you can do things like git.init. It gives you a Git object, add, commit, add tag, all sorts of stuff that you can do with Git. You can do git config, and if you just have 1, it'll give you the value. If you do 2, it'll set the value. You can do log. It'll give you a log of the last 10 commits, and you can, get the parents, the author, dates, times, messages. You can get trees, the subtrees, all the blobs and children and stuff. So it's a really easy way of using Git within a Ruby script. So you can get this at github.com/schacon/ruby-git. And that's pretty much it. So where can you learn more about Git? There are several useful resources. Git.o.cz has a lot of tutorials and man pages and stuff that are very useful. Gitcast.com is a site that I do that has little 5 to 10 minute podcasts that you might be watching this on. You may very well be familiar with it. Delicious has a lot of Git resources in the popular branch that I like to watch. Git and GitHub and RFC are fantastic. The people in those channels are incredibly helpful and very gracious and have helped me countless times. I cannot recommend them enough. Of course, I would like to plug my book, but Jeffrey's screencast is also incredibly well done, and I would highly recommend that. And both the book and screencast sort of support the work that I do on gitcast.com. So you can also email me if you have any questions, and that was really specifically to RailsConf on that last one there. But if you would like to buy me a beer at some point, I would be more than happy to take you up on that. So that's it. You can download the slides from this at gitcast.com/git-talk. And that's all I got. So thank you very much for listening, and I hope this was helpful.